Human rights matter, but conversations about rights can be polarizing, confusing, and frustrating. Lawyers Claudia Flores and Tom Ginsberg have traveled the world getting into the weeds of global human rights debates. On Entitled, a new podcast from the University of Chicago Podcast Network, they use that expertise to explore the stories and thorny questions around why rights matter and what's the matter with rights. Subscribe to Entitled, part of the award-winning University of Chicago Podcast Network. In today's episode, we're going to explore an aspect of the universe that isn't often discussed in popular science. We're not going to be talking about black holes or quantum mechanics or anything like that. Instead, we're going to talk about random motion. The kind of motion that particles in a gas follow, for example, or dust particles in the air. It's something that is so common and so innocuous that you might wonder if it's even interesting. But it turns out that this essential physics of random motion might be the only reason you and I are alive today. The story of how that's possible and a special guest coming up on today's episode. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
To help us explore the significance of random motion, or what we call Brownian motion, we are very excited to invite onto our show our first ever guest, Professor David Grier from NYU.
Hi, Shalma. Hi, Dan. Nice to meet you.
Hello.
Thanks for coming on Why This Universe, David.
Yeah, so I guess some background. We know each other because you taught a class that I took this past spring. You taught me statistical mechanics.
Which is actually one of my absolute favorite classes. It's like such a wild thing that you sort of start off the term by saying, we can't do anything. Physics is hopeless. There's just no, not even a plan to answer all these questions. And then by the end of the term, it's like all these unknowable things are actually kind of obvious. It's just great.
Yeah, that was definitely my favorite class in the spring, so thank you.
Oh, I'm glad. Thank you.
David Grier is an expert in how interesting behavior emerges out of interactions between a bunch of microscopic objects. In a sense, he's helping us understand how order arises out of chaos in the universe. And at the core of this chaos is Brownian motion.
Brownian motion it's actually kind of a principal theme in the branch of physics that I work in. So I work in soft condensed matter physics, which is sort of the search for nature's fundamental organizing principles. Not so much like what is everything made of and what are the fundamental interactions, but rather how do those simple elementary things interacting with each other in comparatively simple ways organize themselves into hierarchies of organization, and where do the properties of those organizations come from? And in some sense, the glue that holds all of that together is Brownian motion. It's a kind of random motion. People call it a random walk. It's the kind of thing that you might have experienced in your everyday life and not really paid much attention to it. So, for example, if you're just lazing around on a sunny day and there's a shaft of sunlight coming into your room, you might see little specks of dust. I'm not so great at sweeping, so I see lots of little specks of dust. You might see little specks of dust floating in the air. And while they're floating around, one of the things you'll notice is that everybody's moving randomly. They're all going in different directions at the same time. Like there may be an overall drift, but on top of that drift, everybody's going in a different direction. And so a question that you might ask is, well, why is that? And it's a really good question to ask, and you wouldn't be the first one to ask it.
So, who was the first person to ask it? Well, the story of Brownian motion starts with an 18th century botanist named Robert Brown. Yes, you heard that right. Brownian motion is not named after a physicist or chemist, but a botanist. So how did that happen?
He was interested in the origin of life. And around that time, people had started making available really good microscopes. So you could like take stuff and put it on a microscope and see what it did. And so he knew that in order for a plant to create a seed, in other words, to generate new life, you needed pollen grains. So he thought, well, let's take a look at what a pollen grain looks like under a microscope. And so he took pollen, put it under a microscope in a drop of water. And what he saw is when he put the pollen grains into the drop of water, tiny little things sort of came fluffing out of the pores in the pollen grain. And each of those tiny little things was moving erratically, like really frantically, like constantly in motion. They're all going different directions. And again, this is all written up in a paper from like 1827 or 1828 in the style of scientific papers from 1827 or 1828, which means that he's saying, you know, on a Thursday last, I had a delightful conversation with the Reverend so-and-so. But so he actually spells out his thought process in a way that we don't anymore. And so what he said was that in seeing this motion, he wondered if this might not actually be the fundamental motion of life. This tendency of these tiny things to move absolutely randomly. Like, could this be what life is? Has he just seen it?
So the discovery of Brownian motion was made because of the pursuit to understand life. It might not be what you expected. After all, we now know that just because particles move around in water doesn't mean that they're alive. And Robert Brown figured that out too.
He was a really good scientist, and he knew that an exceptional proposition requires exceptional evidence. And so he took things that he knew were never alive, like pieces of glass, and he ground them up into fine powders, and he dispersed them in the water, and they did the same random thing. And he concluded from that this has nothing to do with life. But it's still really weird that everything goes, its own magical way. Why, what could be the cause of that? And that's how he ends his paper. And the person who figured it out was Albert Einstein. What he said was, imagine that atoms and molecules really exist. Right? At that time, that wasn't accepted even by the scientific community. Most scientists would have said, well, atoms and molecules are very handy bookkeeping devices for chemists so that you get the proportions right in your reactions, that it's a sort of a good mnemonic, but it's not, these little things don't actually exist. And Einstein said, what if atoms and molecules really exist and they're just too small for us to see? They must be moving. So if they're moving, they have some kinetic energy. And if a tiny atom that you can't see collides with a more macroscopic object that you can see, the big thing will recoil, if only a little bit. Now, we wouldn't be aware of this ordinarily at our very large size because we're being buffeted by these atoms and molecules from all sides simultaneously, and all of those little recoils cancel out. But if an object is small enough, and this is where the statistical mechanics comes in, if an object is small enough, then there's a possibility that you might get more collisions from the left than from the right. And so you'll recoil off to that direction. And then in the next instant, just because of randomness, there might be more collisions from the top than from the bottom. And so you'll move downward. And over time, these fluctuations, these just random rolls of the dice, the flips of the coin, mean that you just not quite perfectly balanced in the number and strength of the collisions from each side. And that would be why the object would move around randomly. It's, in some sense, it's a tracer for the fluctuations of the atoms and molecules that are too small for you to see.
So Einstein did what he did best. He took an idea that was so weird for the time that no one took it seriously and asked what happened if you do take it seriously. That's what he did with the speed of light being constant for his theory of relativity. And now he's doing it for the existence of invisible molecules in order to explain the random motion of the particles that we do see. When you see all those little dust particles moving randomly, what you're really seeing is the effect of them being knocked around by the molecules that make up the air. So it's not that the dust itself can move on its own accord or anything like that. It's just that it's constantly bumping into other invisible molecules. And so seeing the random motion gives us evidence that those invisible molecules really exist. That may not sound super profound to you and me today, but imagine what it was like to experience that discovery for the very first time. But there's a problem. Even though each individual collision of atoms and particles can be modeled with the physics that we know very well, there are just so many atoms and molecules in any macroscopic space that modeling random motion is actually impossible.
Yes, each one of those collisions can be described perfectly well by classical dynamics. But you've got so many of them that you can't keep track. Even if you say, let the atoms and molecules not be interacting, let them just each be going on their own independent way, not colliding with each other, there are still too many of them for you to be able to follow their motions. Then if you further turn on the possibility that they might collide with each other, now it's not just practically impossible, it's rigorously impossible to track their motions, because the sequence of collisions enters you from nice deterministic physics to chaos.
At first, this seems like a huge roadblock. After all, chaos isn't just complicated, it's provably impossible to model. But Einstein, of course, was very clever, and he realized something that would change physics forever. He realized that even if you can't model every particle in your system exactly, you can actually study the average behavior of all of your particles quite well. And doing this means that you can learn new things about your system without understanding it all the way down.
Yeah, it's a random process, so on average, you're equally likely to go left in a time step as you are to go right, and so on average, you don't go anywhere. But as time progresses, you might get like a series of left steps that take you a little bit further afield, then maybe a series of right steps that take you a little bit further afield. So even though you don't go anywhere on average in this Brownian trajectory, you end up covering more ground. So you're staggering around randomly, but you cover and you cover more ground as you give the process more time. And what Einstein worked out is that in some sense the area that you cover should be proportional to the time and not to some other function of the time, not time squared or time cubed or square root of time, just linear. And that dependence of the area that you've covered to the time ought to tell you about, among other things, the temperature. Why is that? Well, the temperature in this atomistic view of things is just a measure of the kinetic energy, the speed of those unseen atoms and molecules. So the hotter they are, the faster they're going. The faster they're going, the hotter they are. And the more your tiny little particle is going to stagger around, faster it goes.
So Einstein showed us how you can study a complicated system of particles statistically and still learn new things about how it'll behave. Out of the chaos of random motion, this predictable average behavior emerges. But to be sure that Einstein's predictions were actually true, some very careful experiments had to be done.
A French physicist, JeanBaptiste Piranha, actually dug in and said, okay, Einstein's made this quantitative prediction for the statistics of this random Brownian motion. Let's see if it's true. And so he did. He published a book in 1912 called Atoms. It's a book about Brownian motion, but tellingly he called it Atoms, where he describes these experiments, where he synthesized micrometer scale spheres of this sort of rubber stuff called gamboge, and he had himself a really nice microscope with a grid in the eyepiece. And so what he would do is he'd look for one of his tiny little gamboge particles. He'd figured out a clever way to measure their diameter very, very precisely, and he'd watch the thing move with a stop. And he had a stopwatch, and so every now and then the stopwatch would go off, and he'd plot a point on the piece of paper, and plot a point on the piece of paper, and so on and so forth, mapping out this random trajectory in even steps in time. And then he took all the data and compared it to Einstein's prediction. And if the prediction's right, then you get two things. You get a measurement of the temperature, that's great, and a measurement of this quantity called Avogadro's number, which is sort of like a dozen, but for a lot of things. It's sort of like an ultra dozen. And lo and behold, the numbers matched. So what that means then is that Einstein had correctly explained Brownian motion as being fluctuations in the unseen sea of atoms and molecules, and it also means that atoms and molecules actually exist.
I imagine that if somebody didn't know the history of this piece of science and they just speculated, like, what was it like to discover atoms, they probably imagined some experiment where, you see an atom or you detect an atom or you bounce something off an atom or something. But it wasn't like that at all. You see this sort of random motion of lots of stuff, and you deduce from the statistics of that motion the presence of their individual pieces. It's very different than I think how most people might have imagined.
No, absolutely. And again, every single test that Einstein conceived of, Piranha actually did the measurement, and they all came together and they all worked. And Piranha actually got a Nobel Prize for this.
So a Nobel Prize did get awarded for Brownian motion, but not to Einstein.
Not well, because he already had enough other stuff. I guess Einstein's great genius, for me at least, the thing that I find most remarkable is not that he was an exceptionally good mathematician, because there are lots of good, exceptionally good mathematicians, but that he said, well, let's not worry about all the complexities. Let's just say it's A plus B times time. Just like throw away everything nonlinear and keep just the linear part and see how that goes. And a remarkable number of his seminal discoveries result from just saying, let's keep it simple and see how that works. And that's why so many different branches of physics have Einstein A and B coefficients.
It's true. It's true.
No, see, it's funny, but it's also true. So, there's a real lesson in that for all of us, right? That it really is. It's great to have the technical horsepower, and to be able to see our science through from first principles to the gory conclusion. But it's very, very helpful along the way to. I wear glasses. If I take off my glasses, you disappear into great simplicity. It's good to take off our intellectual glasses from time to time, and just see if we can't say something simple before we say something complete.
It's kind of beautifully profound, yeah.
Yeah. So far, we've talked about Robert Brown's discovery of Brownian motion, Einstein's theory of atoms and molecules that explained it, and Piranha's experiments that confirmed the theory. But we've moved far from Robert Brown's original research question, the question of what makes life life. From what we've learned, it seems like Brownian motion is almost antithetical to the emergence of life. After all, it's completely random and chaotic. There's practically no order in it at all. But this kind of motion is everywhere in nature. So if all the tiny particles of nature are just bumping around each other randomly, how could it be that complex life forms like you and me can come to exist?
So the question is, from the randomness, this sort of molecular scale randomness, how come organization emerges? How come you and how come we're here, right? So how come our matter is organized into the beautiful three-dimensional structures of biological cells? Now, they're not orderly. They're very disorderly, but they're organized, right? And they have achieved this kind of organization despite this sort of turmoil of Brownian motion. So how did that happen? And the best answer is stay tuned, because we don't know yet, and we're trying to discover.
The core reason that it's so hard to study the emergence of life as a statistical physicist is that we only have well understood laws governing systems that are in a state of equilibrium, as in a system where there's no net flow of energy. A system at equilibrium is stable, and you can say a lot about it quite easily with statistical mechanics. But all this simple equilibrium physics doesn't work at all on systems of life.
We're not in thermodynamic equilibrium. We are consuming energy and producing waste that just as fast as our metabolisms will let us. And somehow or other, that departure from equilibrium allows us to have an emergence of organization that just wouldn't be possible in equilibrium. Equilibrium gives you order, it gives you crystals and beautiful things like that. It doesn't give you the kind of dynamic, kinetic, steady states that make us up. And so I would say we don't know the principles for that yet. But we do know some things. A few of those organizing principles have fallen into place. So sort of underlying this whole line of inquiry is the idea that that yes, I've got random Brownian motion, and it really is random, right? There are no patterns in it. And yet somehow, some processes can extract patterns from that randomness. Another way to say it is somehow or other, these processes are extracting energy, maybe free energy in the thermodynamic sense, but energy from the noise.
The problem with this is, it seems to violate the second law of thermodynamics, at least at first glance. That law that tells us that entropy is always increasing, that there's no way to extract useful energy without using a greater amount of energy. So how is it that life seems to break this law? Well, though it may seem to, organized life doesn't actually break the second law of thermodynamics.
It absolutely doesn't. No. So what it does is like any good cheater, it cheats. So what biological systems have managed to do is not to extract energy from noise, but rather to use noise to extract energy where it ordinarily wouldn't be accessible. That's the interesting thing. So if you think about like a system in mechanical equilibrium, equilibrium in that sense means nothing's moving. All the forces are balanced, so there's no motion at all. And if it weren't for that Brownian motion, well, that's where we'd be. The large things that we're looking at, if the atoms and molecules weren't kicking them around, the large things would just sit on the floor under the influence of gravity, and that would be the end of that. There would be nothing interesting happening. So it's pretty clear the Brownian motion keeps everything aloft, and it keeps everything moving. And by that I mean sampling the energy landscape, the force landscape that's around. The individual proteins aren't like point-like objects. There are these big, extended, floppy, long molecules. And this random Brownian motion keeps them flexing and bending and exploring and trying out different conformations and different configurations and looking around to see if there's anything that might improve their moment in the universe. And without that Brownian motion, that exploration wouldn't happen. And in the process of exploring the possibilities, some of these processes, some of these organizations of matter can indeed extract energy from the outside world and transmute it into something like motion. Again, it wouldn't be possible without the random Brownian motion. It's facilitated by the Brownian motion.
So, in a surprising turn of events, Brownian motion has led us back to Robert Brown's original curiosity. While random motion itself is not fueled by life, it turns out that the emergence of life out of chaos in the universe is only possible because of Brownian motion.
So this is actually kind of a weird thought. Okay, ordinarily, if you've got a machine, like a car engine or something like that, you put in lubricants to make it run smoothly. You want the road to be smooth because you know that any roughness, any randomness, any disorder is going to make your engine less efficient. In the microscopic world, without that randomness, without that roughness, without that disorder, your efficiency would be zero. So these machines need disorder in order for them to go. They need the noise. It's not fair to say that they're extracting energy from the noise, but they're using the noise so that they can extract energy. This Brownian motion is quite clearly at the basis of life. Without it, there wouldn't be life. So any organizing principle that explains life undoubtedly will have Brownian motion as one of its key parts.
So we've talked a lot about the applications of Brownian motion in biology and the study of life, but its usefulness in industry and in our everyday lives extends far beyond just the theory.
There are so many wonderful scientific truths that fly under the radar in our society, and it's such a shame. So there's a state of matter called colloidal dispersions. So we've been talking about small objects floating around in water, for example, and the small objects are the ones that are being buffeted by the atoms and molecules. So it turns out that if you just disperse small objects in a fluid medium, then the Brownian motion keeps them lofted up. It stops them from settling down under gravity. That random motion keeps them dispersed. That's called a colloidal dispersion. And it turns out almost every industry relies on the stability and the properties of colloidal dispersions for the value of what they do. I mean, it's obvious in like paints and food, because a lot of those things are colloidal dispersions. Milk, for example, dairy is a colloidal dispersion of fat and water, basically. Paint is a colloidal dispersion of pigment in some fluid carrier. But I mean, also silt in rivers, like rivers carry silt to fertilize farmland and things like that. That silt is also colloidal. Bacteria, most living things on Earth by both number and mass are bacteria. There's an argument to be made that you and I each individually are more bacteria than we are human, again, by number. And they get from here to there. Their whole transportation process, their life cycle, their existence relies on this Brownian motion that keeps them nicely dispersed. So yeah, at the macromolecular scale, at the organismal scale, throughout technology, Brownian motion is a constant theme. It's what motivates the matter in our lives.
What about the scales that we see in social sciences?
That's really interesting, fascinating. Okay, yes. So a classic example is sort of the random influences that cause the value of stocks to change, the stock prices to change. So if I were to just watch the value of a stock on what I would see is like a random zigzag pattern. Sometimes it runs up, sometimes it runs down. If there's nothing going on that is going to profoundly change the value of the stock, then what you see is essentially Brownian motion in the stock price. And people could claim, oh, I see patterns in that random motion, but I don't know if you've seen the play Rosencrantz and Guildenstern Are Dead, but it's like very unusual to toss a coin a bunch of times and have it always come up heads, right? And just because it has in the past doesn't mean it will in the future, because these things are random, they're unpredictable. So there's a huge part of financial physics that addresses these random processes in financial markets. There's also social physics that addresses random processes in social networks, where you have the randomness and other influences going on at the same time. How do they interact with each other to give you, for example, a flow of opinion through a social network like Facebook? So just as my friends and I are trying to discover principles, we really are trying to discover principles that would explain the emergence of life. Those same principles ought to apply completely generally to things like finance and social networks.
I wonder how often we look at collective behavior in something like the stock market, or in something like election results, or in some other like mass social behavior organization, and we create a story for why those things happened, why that stock went up, why the voters swing one way in a particular election, when really it's no more than Brownian motion, and we're just creating a story after the fact to make sense of it.
So I guess that was the story of the 90s, right? Where the question was, can I look at the history of a random process and infer from that history the underlying dynamical process that was responsible for the signal that I'm measuring? So it's a noisy process, but maybe there's something, maybe there's a machine under the noise that I'm watching. So if I can infer the nature of that machine, maybe I'd understand how that organization will behave in the future given the similar pattern of noise. And this was the origin of a lot of the model building that financial physicists did in the 90s, building trading systems that tried to, as I say, infer the organization of the dynamical system from measurements of past performance. If you are the only person who's trying this, you might have some success. But if everybody's doing this, and if everybody's doing the same thing, these processes are no longer random, they become correlated. And in those correlations came financial disaster. That's not to say that this is the wrong question to ask and the wrong thing to try. It's absolutely worth investigating, because if you do discover that there is order, underlying the randomness, there's an organization in the randomness, then you've probably learned something important.
Thanks for listening to Why This Universe. As a reminder, our Patreon is now up on patreon.com/whythisuniverse. If you want to support us more and get access to some exclusive content and a free sticker, thank you so much for your support. Our show is produced and edited by me, Shalma Wegsman, co-hosted by Professor Dan Hooper of the University of Chicago and Fermilab, and all music is produced by Jake Kleinbaum. Why This Universe is brought to you by the University of Chicago Podcast Network.